Howdy, Papa here. We're continuing with our Rocks of Georgia and adjacent states kind of videos, and today we're going to talk about rock reaction. Now, I just noticed if you look in my glasses, you can see the yard out there. It's a beautiful day. Let's just have a look. Nothing there. Beautiful sunshine. Gonna be hot today. Anyhow, we're talking about rock reaction, and what does that mean? Mineral reaction, rock reaction. That's my name for a classification system that looks at the minerals in rocks and decides whether they're light in color, lightweight with low melting points, or if they are dark in color, heavy in weight, and have high melting points. So let's just look at that rock reaction. If you have rocks with a lot of quartz, which is light colored, a lot of potassium feldspar, which is also light colored, it's white. These are minerals that they're light in color, they're light in weight, relatively speaking. They have low melting points, relatively speaking, 1,000 degrees Fahrenheit, 1,200 degrees Fahrenheit, plus or minus. I'm not sure about that totally. And they make up land crust. Land crust. You know, granite is everywhere you look, and its metamorphic equivalent, granite gneiss, is everywhere you look, and that's the most common rock around on land. And most people just take it for granted, you know? Okay, I'm sorry. So those quartz and potassium feldspar, and to some extent sodium feldspar, are considered felsic minerals. Felsic. We already talked about why felsic, because feldspar, sic, and that's, I guess, means silicon for quartz. Felsic. So if your buddy Bobby Joe got sick, if he fell sick, he would be white. He'd be pale. So that's how you remember felsic rocks are lightweight. Now let's skip over to mafic rocks. Mafic stands for Mafic stands for magnesium element, and fic stands for iron. Both of these are heavy elements, dark colored elements. So we're talking about mafic rocks. They're dark, they're heavy, they have very high melting points. It takes a lot of heat to melt them, and they are found in the ocean bottom, not the sediments, but below the sediments. Ocean crust. Ocean crust is made of mafic rocks. Examples of mafic rocks: your basalt lava, the Hawaii lava that we all know about, is a mafic rock, and that's what mostly ocean crust is made out of. The stuff is heavy, that's why it sinks down to become the ocean crust. The felsic rocks are light, and that's why they rise up, float up, literally, relatively speaking, for rocks to form the land crust. So these mafic rocks have a lot of iron and a lot of magnesium in them. They have a lot less quartz in them than the felsic rocks, like granite. Also, these mafic rocks, these dark mafic rocks, have a lot of calcium feldspar, not so much sodium feldspar, and probably no potassium feldspar in them. So you can kind of say in your mind, generally speaking, potassium feldspar is a felsic mineral, sodium feldspar is an intermediate mineral, calcium feldspar is a mafic mineral. Okay, so we talked about felsic, land crust, mafic, ocean crust. Let's go back toward felsic into, if you go halfway back from mafic to felsic, you're an intermediate. We call these intermediate rocks. Rocks with an intermediate reaction. And intermediate rocks are also found on land. So you have felsic rocks that are land crust and intermediate rocks that are land crust. You find these intermediate rocks, especially when you get subduction zones and island arc volcanoes. An example of intermediate rocks is diorite lava and andesite lava. You've heard of the Andes Mountains in South America? Well, they were named after this andesite lava, which is very common there. These intermediate rocks They're kind of speckly, light and dark speckly. They can also be gray. They can be light gray. They can be dark gray. They can be reddish if they have a lot of iron in them, but they're not dark and they're not heavy, and you find them mostly on land, not in the ocean crust. We're talking of intermediate minerals. We're talking mostly biotite, talking sodium feldspar. If you take those two and then you add a little bit from the felsic land crust, like quartz, and maybe a wee bit of potassium feldspar, and you add a little bit from the mafic ocean crust, which would be a little iron and a little magnesium, then you get these intermediate rocks. So biotite gneiss is a metamorphic version of these intermediate rocks, and this diorite magma, which becomes andesite lava when it erupts, you metamorphose this stuff and you've got biotite hornblende gneiss. Hornblende is also a mineral that can be intermediate to mafic. So we have felsic rocks, land crust, intermediate rocks, also land crust, especially island art situations like the islands of Japan and the Aleutian Islands. And then you've got mafic rocks, which is ocean crust. Now let's go down deeper into the mantle. The mantle is that molten part way down below the ocean crust, 10 miles, 20 miles deep. And it's the most common, it's the largest hunk of rock, molten, plasticky molten rock there is. And now we're talking about ultramafic rocks. Ultramafic, super heavy. They're dark. Their melting points are super duper high. And so let's have an example. Let's talk about ultramafic minerals, iron and magnesium. I mean, those are ultramafic elements. They make ultramafic minerals, which are olivine, which is a greenish mineral, and pyroxene, which is a black mineral. These produce rocks like Dynite and peridotite. Dynite and peridotite are very similar. They're rocks that are chock full of iron and magnesium. They have calcium in them. They don't have hardly any silicon at all. Silicon's too lightweight. It just pops up and floats up to the land. So Dynite / peridotite. Dynite is just peridotite that has a whole lot more olivine, like 90% olivine mineral in it. That's the most common rock on the planet because the whole molten mantle is made out of this peridotite / Dynite, whatever you want to call it. Okay, so there are times and places where this peridotite / Dynite comes in contact with ocean water. In subduction zones, it does, and in rifting areas, it does too, because, you know, our rifting areas either start out or end up in the ocean with a mid-ocean ridge, and ocean water gets down there. So when you combine peridotite / Dynite with ocean water, you get serpentonite, which is a greenish, whitish, ultramafic rock that is basically olivine mixed with water chemically, and it is soft. Soapstone is another name for it. You've heard of soapstone, which is a soft rock. And so where do you find the soapstone? You find this serpentonite / soapstone / talcum powder, same stuff. Asbestos, same stuff, different form. And you know, I'll talk about asbestos when I show you pictures of these rocks in the next video. You find the soapstone or serpentonite in subduction. You find it at mid-ocean ridges because the basalt lava, the ocean water gets down into these mid-ocean ridges, combines with the peridotite of the mantle and forms this soapstone. So there's a lot of soapstone globbing around in ocean crust. Also, when the ocean crust gets into a subduction zone, there's a lot of seawater is taken down into the subduction zone, so you get even more soapstone, and the soapstone rises up because it's slick and greasy and so it slides up out of the subduction zone and helps the subducting piece of ocean crust slide down into the mantle more easily. If there's not a lot of serpentonite formed in these subduction zones, then that's when you get your big massive earthquakes like in San Francisco earthquakes, California, where the Pacific Ocean plate is subducting underneath the land. In places like San Francisco, there's not a lot of serpentonite down there to make that process slick, so it gets the ocean crust gets stuck. It's trying to push down and it gets stuck and it's stuck and stuck. Finally, it builds up enough pressure to where it's released, so it goes kablam, slides down maybe 10 feet and causes an earthquake. In other parts of California, there's a lot of serpentonite, so the ocean crust just goes sliding down nice and slick. And that's also why in California, serpentonite is the state rock of California, because it's everywhere in the coast ranges. The coast ranges are the material that got scraped off of the ocean crust as it plunged down underneath the west coast in California and shoved up a bunch of this serpentonite on land. So if you go to the coast ranges, you can find this soft, greenish, slick, shiny serpentonite in many places there. And I'm going to show you some soapstone in the one of the next videos that you see here. You don't find the slicky serpentonite here in the east, but we do have it where ocean crust has been shoved up on land. So that's rock reaction. I hope it makes sense. Have a great day. Papa out.